Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 4. Section 1, Chapter 7, Topic 4. Understanding strain life equations in semiconductor packaging. Introduction. Strain life equations, also known as epsilon n curves, play a critical role in predicting the fatigue life of semiconductor packaging materials subjected to cyclic loading conditions. These equations provide valuable insights into the relationship between strain amplitude and the number of cycles to failure, helping engineers assess the durability and reliability of electronic devices. This overview explores the principles, applications, limitations, and implications of strain life equations in the context of semiconductor packaging. Principles of strain life equations. Strain life equations quantify the fatigue behavior of materials by establishing a relationship between applied strain amplitude, epsilon, and the number of cycles to failure, n. The key principles of strain life equations include fatigue strength. The fatigue strength represents the maximum strain amplitude that a material can withstand for a specified number of cycles without experiencing fatigue failure. Endurance limit. Similar to stress life, SN, curves, strain life curves may exhibit an endurance limit, indicating the strain level below which fatigue failure does not occur, even after an infinite number of cycles. Fatigue life. The fatigue life corresponds to the number of cycles at which failure occurs for a given strain amplitude, typically plotted on a logarithmic scale against strain amplitude to produce an epsilon n curve. Strain rate dependency. Strain life equations may account for strain rate dependencies, where the fatigue behavior varies with loading rates, temperature, and environmental conditions. Applications of strain life equations in semiconductor packaging. Strain life equations find various applications in semiconductor packaging for predicting fatigue life, assessing reliability, and optimizing design. Material selection. Strain life curves aid in selecting materials with appropriate fatigue properties, such as high fatigue strength, endurance limit, and resistance to crack initiation and propagation, to minimize fatigue-related failures in semiconductor packaging. Design optimization. Engineers use strain life equations to optimize package designs, component geometries, and material selections to reduce strain concentrations, extend fatigue life, and enhance package reliability. Fatigue testing. Experimental fatigue testing generates strain life data for specific materials and loading conditions, validating predictive models, calibrating design parameters, and estimating fatigue life under real-world operating conditions. Reliability prediction. Strain life equations serve as inputs for reliability prediction models, such as finite element analysis, phi, damage accumulation models, and probabilistic fatigue life estimation techniques, to assess the probability of fatigue failure and design robust semiconductor packages. Limitations and considerations. While strain life equations provide valuable insights into fatigue behavior, they have certain limitations and considerations. Simplified assumptions. Strain life equations are based on simplified assumptions, such as constant amplitude loading, uniform stress distributions, and idealized material properties, which may not accurately represent real-world conditions. Material variability. Strain life curves may exhibit scatter due to material variability, manufacturing processes, surface finish, environmental conditions, and other factors, necessitating statistical analysis and uncertainty quantification. Environment effects. Strain life curves are influenced by environmental factors, such as temperature, humidity, corrosive agents, and chemical exposure, which can accelerate fatigue degradation and reduce package reliability. Loading conditions. Strain life equations may not account for complex loading conditions, such as multi-axial loading, variable amplitude loading, or time-dependent loading, requiring additional modeling and experimental validation. Experimental methods for generating strain life data. Experimental techniques for generating strain life data include axial fatigue testing. Axial fatigue testing applies cyclic axial loading to specimens, measuring strain responses and fatigue life under controlled loading conditions. Biaxial and multi-axial fatigue testing. Biaxial and multi-axial fatigue testing subject specimens to combined axial and transverse loading, simulating real-world loading conditions and assessing fatigue behavior in complex stress states. Variable amplitude fatigue testing. Variable amplitude fatigue testing applies cyclic loading with varying amplitudes and frequencies, mimicking realistic loading conditions and assessing fatigue life under service-like conditions. Accelerated testing. Accelerated testing methods, such as accelerated life testing, ALT, and accelerated stress testing, AST, subject specimens to accelerated loading conditions to predict long-term fatigue behavior and estimate service life. Conclusion. Strain life equations are essential tools for predicting fatigue life, assessing reliability, and optimizing design in semiconductor packaging. By understanding the principles, applications, limitations, and experimental methods associated with strain life equations, engineers can make informed decisions to optimize package design, select materials, conduct fatigue testing, and improve reliability prediction for semiconductor packaging. Continued research and development in fatigue modeling, experimental testing, and reliability assessment will further advance the understanding and mitigation of fatigue-related failures in semiconductor packaging, ensuring the continued reliability and durability of electronic devices. Thanks for watching. Please like, share, and subscribe.